Hello students! Since we didn't get to finish all of our equations in class, I wanted to take a moment to go through several equations with you. Alrighty, so we're going to start actually at the back end and we're going to look at problem 5, which is the log base 2 of x squared minus x minus 16 equals 2. So the first thing we're asked to do is actually identify what type of equation this is. And it's pretty self-explanatory. This one's a logarithmic equation, right? And what specifically makes it a logarithmic equation is the fact that not only does it involve a logarithm, but that the variable x is within that logarithm itself. Notice where it's at. It's inside that logarithm. And so that aspect of it causes it to be called a logarithmic equation. What is our main goal when we're trying to solve logarithmic equations? Well, obviously, the main goal is to get the x outside of the logarithm, right? We want to get it out of the logarithm. And that becomes our focus, our key focus, as we move forward and perform some algebraic operations. One other thing I asked us to consider before we actually got into the business of solving our equations was look for where or consider where these equations are used or applied in our STEM contexts. And there are several places, many places where you'll see logarithms. You'll see them all over calculus. But if you want to think more scientific, anytime you talk about like Richter scales, the Richter value on an earthquake, you're talking with logarithms. Whenever you talk about the temperature of a coffee cup, the coffee within a cup as it cools over time, you're going to be involving logarithms. It's very much related to exponential growth. And so if we think about probably one of our most recent pandemics, the COVID pandemic, it was going on an exponential growth curve and our government tried to stop it. The scientists, they worked together and they put in place a lot of restrictions with the hope that even though the virus was going, it changed from an exponential behavior into more of a logarithmic curve. And so there are many instances when you are looking at logarithms in science and STEM courses as well as calculus. So they're fundamental and understanding them becomes really important. So let's actually talk logarithms. How would we solve a logarithmic equation and get the x outside of that logarithm? Well, remember, logarithms are themselves exponents. And there is a fundamental definition that relates logarithms to exponents. And let's write it down here. So suppose I have a logarithm with a base b, and that logarithm is taking a logarithm of something, right? A logarithm, let's say, base b of a number n. And let's say that logarithm is, in fact, m. Well, like I said, a logarithm is an exponent, and so a key way to think of it is in terms of its equivalent exponential equation. This is the same statement as saying b to the mth power equals n. Using logarithms allows us to work with exponents. And so they go hand in hand with exponents. Log base b of n equals m is equivalent to the statement that b raised to the mth power is n. And this is a crucial need-to-know fact. This is one thing you need to know as you move forward in your engineering, STEM, or calculus courses. Okay, so now that we have that background, it's time to get in and solve this logarithmic equation. So I'm going to rewrite that logarithmic equation as log base 2 of x squared minus x minus 16 equals 2. And remembering our goal of getting x out of the logarithm, I want to immediately rewrite this logarithmic equation as its exponential form, or in its exponential form. Now, how do we do that? Again, we want to pay attention. Your base is always located down in the base, so that will be my base. So this logarithmic equation translates into 2 being my base. And then notice my exponent in the logarithmic equation is actually the result on the right side of a logarithmic equation. And so that means that right here, this 2 on this side actually becomes my exponent. And then the n, the object that's within the logarithm itself, that is the result of raising b to the nth power. So this right here is actually my result of raising b to the nth power. And so by simply using the exponential equivalency of a logarithm statement, I have created this equation. 2 to the second equals x squared minus x minus 16. Now, we are good to go because we no longer have a logarithm in our statement. We have gotten the x out of the logarithm. And what has resulted is, what do we call this? This is a what kind of equation? This is a quadratic equation. And we note that because it has a power 2 on it, right? It's got, oh, sorry about that. It has the highest degree being a 2. It's a polynomial equation, specifically one of the second degree, right? And how do we solve, just reminding ourselves in the thought bubble, how do we solve quadratic equations, specifically polynomial equations of the second degree? Well, there's 2 main methods that we discussed in class. One was factoring, and then if factoring fails or we are unable to do so, we apply the quadratic formula. Now, we can always use the quadratic formula, but sometimes it gets a little messy, and so if we can factor, we factor first. That is exactly what I'm going to do. But before I factor, connecting to another thought bubble, right, is the idea that in order to use factoring, I have to recall the zero factor property. In other words, factoring goes hand in hand with the idea that factoring only helps us provided those factors are set equal to 0, right? And the zero factor property helps us because then we know that if we're multiplying 2 objects, either the first object is 0 or the second object has to be 0. There's no other way to multiply 2 numbers to get 0. So the zero factor property, that idea, combined with factoring, is going to help us solve this equation. It also sets the stage for our next logical step in this process, which is I need to rework this equation using algebraic and properties of equality to convert this equation, this quadratic equation, into being an equation that is factored and set equal to 0. But in the reverse order. Let's first set it equal to 0. Now, I note on the right side, I have a positive x squared, and so I'm actually going to bring all of my terms from the left to the right. And before I do that, let me do one step and clean this up. 2 squared is just 2 times 2, which is just 4. And so I'm going to rewrite this equation as 4 equals x squared minus x minus 16. And now I'm going to proceed to get a 0 on the left side because I want to keep my x squared positive. That's me. You could do it the other way, but I like to keep my x squared positive. And that entails us using the additive property of equality where we're actually adding a negative number to both sides, giving us a 0 on the left, and on the right we have x squared minus x minus 20. We are now lined up to apply our zero factor property, but my brain likes to put that 0 on the right. You don't have to, but my brain likes to do that. So I'm just going to put my 0 on the right instead of the left. And so x squared minus x minus 20 equals 0. We're going to factor. Factoring involves finding 2 numbers that multiply to negative 20, but add to that middle coefficient, and I'm going to reinforce that middle coefficient is a negative 1. It's understood to be a negative 1. So I'm looking for 2 numbers that multiply to negative 20, but add to negative 1. Well, let's see. What 2 numbers do that? Oh, negative 20. I've got 2 numbers that multiply to negative 20. 5 and 4 give me positive 20. And if I add them up, where one is positive and one is negative, it's going to give me that -1. And in fact, I think the combination is if I have a -5 times a 4, I multiply them to get -20, but I add them to get -1, and so I think those are my key numbers, my magic numbers. And that then allows us to factor this trinomial into two binomials with x times x being our first terms, followed by -5 and then +4, which if we were to go back and FOIL it out, we would discover we would obtain x squared minus x minus 20. Whew. Alrighty, we have completed the hard part, which is we've removed the x from the logarithm. We noticed we had a quadratic equation, we factored, we set it equal to 0, and the very last step then would be to apply our zero factor property, which means we're going to set each of these equations, each of these terms, each of these factors, I should say, not terms, but each of these factors, set them equal to 0. The first one has got to be 0 or the second one. And that means that the first one, or x has to be from the first factor 5, and the value of x that would make the second factor 0 is -4. And so I have two proposed solutions to this logarithmic equation. Alrighty, so the question is, are we done? Like have we finished what we need to do? Well, we have to be really careful when it comes to logarithm equations, square root equations involving square roots, equations involving rational expressions, because sometimes we get what are called extraneous solutions. In our process of solving, we create solutions that algebraically make sense, but when we go back to put them in our original equation, don't satisfy that original equation, due either to domain restrictions or simply the process yielded for us a result that wasn't true, our algebraic solving process. So we need to check our extraneous solutions, specifically when we have logarithm, radical, and rational equations. And checking means we're going to take our solutions and we're going to put them back into our original equation. So I am going to take my log base 2, and in place of x, I'm going to put 5. Now, our equations are pretty simple. It shouldn't take too much effort to look at this. And let's see, this means I have log base 2 of 5 squared is 5 times 5, which is 25. And then I'm going to subtract -5 and -16. So that means I have log base 2 of, and let's see, what is that, 20 minus 16, which is 4. And so my question is this a true statement? Well, yeah, because we know that base 2, raised to the second power, so base 2 raised to the second power, rewriting this as an exponential equation form, is 4, and that is true. And so yes, x equals 5 is a true solution, and it satisfies our original equation. We want to check our other solution that we obtained, x equals -4 now, and see if we get a similar result, something that is in fact true. Well, let's see. Log base 2 of -4 squared minus -4 minus 16, does that equal 2? So we have log base 2 of, what's in here, 16 plus 4 minus 16 equals 2. And again, we get a similar situation. Everything is beautiful. We wind up at the same state we were before. Log base 2 of 4 is 2. Or in other words, 2 to the 2 equals 4, and everything is hunky-dory. And x equals -4 is also a true solution. So that means there are two solutions to our original logarithmic equation, x equals 5 and x equals -4. And we can be confident when we put those answers in WebWork that it's going to give us green. Absolutely. Sometimes I do want to note one thing. Okay, because not everybody has the same equations, and I'm not sure on your homework if you get any that has extraneous. So let me just put this extra note here just to be aware of. Okay, if you were to result in a negative number inside this quantity, so if there was a negative number inside this quantity, that is a situation where you have extraneous solutions. That is because logarithms, by their definition, have a domain where all of the values within the logarithm must be positive only values. No zeros, no negative numbers. Everything that's inside a logarithm has to be positive only. And so when you're checking your solutions, if you happen to wind up with something that creates a value inside a logarithm that is not positive and doesn't check out, then it will be extraneous. All right, well, good luck with all your studies. I hope your logarithm solving goes well, and if you have any questions, don't hesitate to reach out.